Welcome to Unwired Learning. In this video, we're going to talk about the process of ambipolar transport. We're going to explain the process of ambipolar transport. In particular, ambipolar transport is applicable to what we call excess carriers, the carriers above and beyond the thermal equilibrium values that we have previously used for things like drift current and diffusion current. And at the end of the video, we're going to solve a classical example of ambipolar transport. Over here on the left, you can see that I have a picture of some reason why you might have excess carriers in a semiconductor. Imagine this blue rectangle here is a semiconductor material, doped at some level perhaps, and what we do is we shine light on that material. Now, if it's the right kind of semiconductor and the wavelength of the light is correct as well, we have a chance of generating excess carriers in this system. Now, the question we would have is, well, how do those carriers move with time? If we think about it and we have excess carriers over here on the left, well, that means we have a higher concentration of carriers on the left, and they're going to want to diffuse across this semiconductor. Well, as they diffuse, there's some other things that might happen, right? The carriers will only last so long before they might recombine. In addition, we might continue to have generation over here. So what we want to know is things like, well, how long does it take to equalize and have a homogeneous distribution of carriers throughout the system? At any given time, what does the distribution of carriers look like? There's so many questions that we could ask. Of course, also, if we have carriers moving across the semiconductor, that means that we have current in the semiconductor. So we might want to know, well, what kind of current values do we have? So there's so many questions that could be asked about excess carriers, and that is the process of learning about this phenomenon we call ambipolar transport. Before we can begin to really look at the ambipolar transport equations, let's look at the idea of continuity. And what we're thinking about here is we're thinking about a volume. Let's take a cubic volume here, a dx, a dy, and a dz here. And what we want to do is we want to look at what is the flux of carriers coming in on the left side, and how does that flux change? Does it increase or does it decrease across this volume? And when we do that, we can start to understand how we can develop equations that represent the current or the flow or flux of carriers through this system. In this case, I'm simply going to look at holes, but recognize that if I look at one of the carriers, it is applicable to the other carrier as well. All the discussions that we have about holes here will be applied equally to that of electrons. So as mentioned before, there's a lot of things that can happen within this volume. We know that we could have generation within this volume. Generation of carriers due to maybe excess thermal energy, or maybe light in this system, or even perhaps some injection of carriers in some other form, as we'll see in a device that we'll call the p-n junction later. At the same time, as the carriers are being generated, we might also recognize that they can recombine, right? They're only going to be in a high energy state, in that conduction band state, for so long before they recombine. And so all of these things can happen within that time that these particles are in this volume. At the same time, we also might have carriers that are drifting or diffusing across this semiconductor that this volume is taken from, and we might have some incoming particle flux, some initial flux coming in on the left side. So we need to take all of these ideas into account in order to have full continuity of what is happening within this volume. So let's look at this. What we want to know is what is the change in the total number of carriers in time. So let's write that. We can say, well, we want the partial derivative or the change of the carriers in time. In this case, I'm writing P. P actually can represent both thermal carriers as well as the excess carriers. So it's not just the excess carriers that we're considering right now. And as mentioned before, we could have some flux of carriers coming in, and we'll represent that as a change in flux, right? We can see here, if we have a differential volume dx here, then it's going to be the change in carriers across that system that we want to consider. So let's write that as equal to minus df of p dx. Now, if we generate carriers within this volume, that is an addition of the total number of carriers that we'll have with time. So we should add that. So we'll add generation, we'll call it plus G sub P. And if we have recombination, maybe they only make it part of the way and then they recombine, in which case they're no longer going to go through this other edge of this differential volume. So what we have is we have some time constant, some average length of time that these carriers can go before they fall into, in this case, if it's a hole, before they recombine with the electron. So we'll write that as minus P divided by the time constant tau sub pt. Similarly, for electrons, we can write a very similar looking equation. We can say dn dt equals minus df sub n dx plus g sub n minus n over tau n of t. All right, so what I've done here is I've rewritten the equation here that we have called the continuity equation here for holes. It includes our time rate of change of the number of carriers in this differential volume, and the flux and the generation rate and the recombination of the carriers in that volume. But let's expand this with what we know about how carriers act in a semiconductor and the different forces that we can apply. So we know that there's a couple of things that we could have. We could have a drift force or an electric field force that could cause the carriers to drift across this volume. We also have diffusion forces that could happen. If we have unequal distribution of carriers across a volume, then we'll have diffusion in that system. So this is all very familiar to us. Let's remind ourselves of the drift and diffusion current equations, and we're just going to write it down here for holes in this case. So we can say that Jp, the current density of holes, is equal to the electronic charge E times mu sub p times the total number of carriers P times the electric field minus E times the diffusion constant d of P times the spatial rate of change dp dx. Now let's look at this and we might remind ourselves, hey, actually, this is a familiar quantity. This idea of current density is actually hardly any different than particle flux. The only difference between particle flux and current density is the fact that we have a charge rate here, or a charge value here. So what we can do is we can actually divide by the charge on both sides of this equation, and we actually have a flux. When we do that, we find that our flux, F sub p plus, is equal to mu sub p times E minus d sub p times dp dx. All right, so let's look at this equation now. We can see here we're almost ready to plug this back in. We just need to take the divergence here, or the derivative of this flux value, and then plug that back in, and we can start to expand this continuity equation, and we start the development of what we call the ambipolar transport equation. We can know that our number of holes here, or the carrier density across this volume or across this semiconductor, might change. So this is a function of x. As well as the electric field. The electric field might change as a function of x as well. So we do need to take the divergence of these, or the first derivative here. Then we look over here, we already have a divergence or a derivative here of p dp dx. So as we take the derivative again, we're going to end up with a second derivative here in the diffusion term. So let's go ahead and write this out. We can write that Fp plus is equal to mu p times dp E dx minus dp times the second derivative dp squared dx squared. Now this term here might be a little concerning to some, so let's focus our attention a little bit on this guy and let's see what we can do. Now if we limit ourselves to taking our derivatives in one dimension in the x direction, then I hope we can see that these two values here are linearly separable. So we can say that the dpe dx term is equal to the electric field times dp dx plus p de dx using the chain rule. Now that we have our flux term here and we have our expanded first term, I think we're ready to start plugging this back into our continuity equation. So rather than voice this all out, I'm just going to write it out. Here we have our continuity equation. But we should take a look at a couple of these terms here. We should look at these terms here for the time rate of change of carriers as well as the diffusion term here. And we should consider whether these things, because we know that P equals the thermal equilibrium concentration plus the excess carriers. We should consider each one of these terms and consider if there's something that we can do to simplify this. Well, let's look at the time rate of change here. And we can see, well, thermal equilibrium carriers, if we have a homogeneous semiconductor or homogeneous semiconductor, then we know that the time rate of change is actually independent. This portion is independent of time, whereas the excess carriers is not. So we can write this first term as only with respect to the excess carriers. So we can write d delta p dt. Similarly, for this diffusion term here, we can recognize that if we have a homogeneous semiconductor, then we don't have diffusion that is caused by the thermal equilibrium carriers. Rather, any diffusion that we have in the system is only going to be caused by the excess carriers. So we can write this first term here on the right side also as dp d squared delta p dx squared. Now when it comes to this drift term here where we have the electric field, if we're looking here at a spatial change in the carriers, but we have a homogeneous semiconductor, then we can also say that the thermal equilibrium carriers are not a function here of x. So we can write minus mu sub p times the quantity of E d delta p dx. Now when it comes to this term here with the spatial change in the electric field, we do actually still have to take into account all the carriers in the system here. We're not taking a derivative here, so there's no terms canceled out. So this term remains the same. The generation term will remain the same. And here we don't take any derivatives or anything like that either. So this term also remains the same. So finishing this out, we can say plus p de dx into quantity plus gp minus p over tau pt. A similar equation can also be developed for the electrons in the system, and as you might imagine, most of the terms are exactly the same, except we're going to replace p's with n's, and that's about it. So now let's look at the development of the full ambipolar transport equation, starting with the continuity equations that we just developed. And here, just for the sake of it, I've rewritten these equations out for us. Let's first start with the idea of excess carrier. So imagine this positive carrier and this negative carrier here are excess carriers. And let's imagine that what we try to do is we try to have an external applied field to that system. Now, if we do that, what we would find is that these electrons here, they would be attracted to the positive side of this field, and these positive carriers, they'd be attracted to the negative side of this field. But because these excess carriers occur in pairs, as soon as we start to separate these carriers because of the external applied field, that generates an internal applied field, which once these carriers come back together, they attract each other when they try to separate. In practical terms, what all this means is that actually when we look at the transport of excess carriers, right, the movement of excess carriers in a semiconductor system, it turns out that the positive and negative carriers, they move together, they drift together, they diffuse together. Well, that means since they're moved together, one of the things that we're going to do here to develop our ambipolar transport equation, well, we're going to put these two equations, these two continuity equations, the one here for holes and the one here for electrons, we're going to put those together. Before we do that, let's simplify a few things, a few ideas. Let's look at these recombination terms here. Well, we know from previous that the recombination rates for electrons and holes, especially since they're moving together, well, they're going to be exactly the same. So we can say that Rp equals Rn, which equals R. Now let's take a look at these generation terms here. Again, for the same reason that we have the recombination terms equal each other, because these carriers are moving together, there's no reason to believe that these generation would actually be different, so there's no reason to write G sub P or G sub N. We'll just simply write G. All right, now for our first process of trying to put these things together. So one of the things we might notice is that on the top equation we have a mu P and a P, and on the bottom equation we have a mu N and an N in quite a few of the terms. So if we actually multiply the top equation on both sides by mu NN and the bottom equation on both sides by mu PP, that's going to be a good step towards simplifying this equation down. All right, so now let's look at putting these two equations together. And what we're going to first do is we're going to add these two terms together. Now, since we multiplied top and bottom by mu sub NN and the bottom by mu sub PP, when we look at this, what we're going to have is we're going to have mu sub NN times dP plus a mu sub PP d sub n. And then that's going to be times our derivative terms. Now, one of the things we might notice here is that we have a delta P here and a delta N here. But again, since our electron and hole access carriers are moving together, there's no need to distinguish these. So we're just going to write delta N as 1. We could have chosen delta P, it doesn't matter. So again, that leads us to mu sub NN times dP plus mu sub PP times dN, and that whole quantity times the second derivative of delta N dx squared. All right, again for our next term, we're going to have mu N mu P times N plus mu N mu P times P, all that whole quantity times the electric field and the first derivative of the excess carriers. Now we have to watch our negative up here and our positive up here, and so if we're careful about that, then we're going to find that we get plus the quantity of mu P mu N times P minus mu P mu N N. That quantity times the electric field times the first derivative d delta N dx. All right, now let's see, up here we're going to have a negative P d dE dx and also the mu NN, and then on the bottom we're going to have a positive mu N mu PP times N dE dx. Well, actually, look at that. That means that this term, when we expand these out with these extra multiples out here, in this term, they're exactly the same terms, and one is minus, one is positive, so therefore they cancel each other out. So that means we can move over here to our generation term, and here we're going to have mu NN plus mu PP times our generation term. So again, that's mu NN plus mu PP times our generation term. Very similar here for our recombination term, except that we just need to account for the fact that we have a minus on both of these. So we have minus mu NN plus mu PP times our recombination. And similarly for our right-hand side of our equation, we're going to have mu NN plus mu PP times d delta N dt. Now, hopefully we can see that we have quite a few instances of mu NN mu PP, mu NN mu PP, mu NN mu PP, and therefore this is a good opportunity to go ahead and divide both sides of the equation by that quantity, and it will simplify this around a little bit. So our first term, rather complicated, but it's going to be mu NN dP plus mu PP dN divided by mu NN plus mu PP times the second derivative of the excess carriers with respect to x. And for our second term, we're going to have plus mu P mu N times P minus N divided by mu NN plus mu PP. And that's going to be times the electric field plus the first derivative of delta N with respect to x. And then we have our generation term plus G, our recombination term minus R, and that is equal to the time rate of change of our excess carriers. All right, now looking at this first term, hopefully we can see that we have mu N, N, and mu PP on the top, and we have that same thing on the bottom. So the any of the units for mu N and N, they cancel each other out, and effectively we just have a couple of diffusion terms that are being added here. So the units of this quantity here is diffusion. So what we're going to do is we're going to simplify that. We're just going to say that's a modified or a new diffusion term d prime. Similarly, over here for our second term, what we have is we have a mu and a mu multiplied, and that's divided by a couple of mu's being added. Never mind the p's and the n's. Actually, you can see that the units there for p's and n's will cancel each other, but we have a square of the mu units, and we have a sum of the mu units on the bottom. So in total, the quantity up here is a mobility unit-wise, and so we're going to call this mu prime. All right, now that we have that, we can simplify our equation down, and we can say that d prime times the second derivative of excess carriers plus mu prime times the electric field E times the first partial of our excess carriers with respect to x plus g minus r equals the first partial derivative with respect to time of our excess carriers. And with that, we have our total ambipolar transport equation. Now, oftentimes what we're going to find is that we can simplify this guy down. If we actually look at this equation up here, it turns out that oftentimes these equations will simplify down, and we don't necessarily have to use this more complicated, which, we've simplified here, but it's a more complicated equation. In the same sense, this term over here for mobility, if we have a p-type semiconductor and we have low injection, it's much smaller than the thermal equilibrium value of excess carriers, then here we can see that our p term will dominate this n term, and down here at the bottom again, our p term will dominate this n term, and so this thing will simplify down. In fact, this one's easy to see, right? If this is negligible, and then we have the n here is negligible, then we have our p's will cancel and our mu p's will cancel, and all we're going to be left with is our mu sub n. That's actually important to understand because, in fact, look, the mu sub n is what's left over, and so our mobility of our carriers, our excess carriers, is actually dependent on the minority carrier. All right, now let's look at an ambipolar transport equation example here. Well, not really an equation example, but let's look at an example of applying ambipolar transport to a problem. So in this problem, we have an N-type semiconductor. Let's just say it's silicon and it's at room temperature 300 degrees Kelvin. And it may not be obvious here, but I'm drawing this all one in color to indicate that I have a homogeneous distribution of our donor dopants here. And let's say that our donor dopant value is 10 to the 16 per cubic centimeter. And in this case, we are going to shine some light on this guy, let's just say, and we're going to simplify matters. Now, we might recognize, of course, that if we're shining light on one side of this semiconductor, then we're going to generate carriers on that surface, and then they're going to diffuse down. But for the sake of making our problem a little bit easier, let's say that this is very thin, and let's say that our light, can penetrate down to that depth, and let's just say that we have a homogeneous generation of carriers throughout this entire semiconductor. So our generation is not dependent on a spatial dimension here. And what we want to look at is we want to look at the time rate of change. We want to look at how does the excess carriers change with time. Let's say, what we want to do is we want to look at the semiconductor right before we turn the light on, and then we want to look at the time right after we turn this light on. What happens in that brief moment in time when we turn that light on? How does the number of excess carriers change, and what does that time graph look like? All right, so over here we have our N-type ambipolar transport equation. We have the full equation, but just specifically for a homogeneously doped N-type semiconductor. Well, that's what we have, so that's good. So our problem states that we want to find the expression for our carriers with time, our excess carriers with time, and then we want to plot that value. So in this case, if we have a distribution of carriers that's occurring throughout the thickness, and we have a generation of carriers throughout this thickness, then we will not have a diffusion term. So our diffusion term goes away. And the reason for that is uniform generation. All right, also in this particular semiconductor, we don't see any external applied electric fields or no, external voltages or anything like that. So it looks like we do not have an electric field. Our electric field is 0, so this next term is also 0. All right, so what does that leave us with now? That leaves us with a generation, a recombination, and then our time rate of change of our excess carriers. And so let's rewrite that down here. We can say that G prime minus delta P over tau P naught equals d delta P dt. All right, so let's look at this particular guy. So we can see here that what we have is a first order partial differential equation. And instead of solving this particular differential equation, I'm just going to write the form of the solution. Well, not actually the form of the solution, but the actual solution for this particular case. So we can write delta P of t equals G prime tau P naught times 1 minus e to the power of minus t over tau P naught. All right, now looking at this particular equation, we can see this first term, this g prime t times t, right, this tau p naught, well, that's the generation of carriers with time. And this last term, this e to the minus t over tau, well, that's going to be how we indicate our recombination, right, because it's subtracting from our total number of carriers in the system. Couple of things that we can look at now. Let's look at what this value is at time t equals 0. Well, if we have time t equals 0, then we can see that this is e to the minus 0. Well, e to the 0 minus 0, whatever. Well, that's just 1. So we have 1 minus 1, which equals 0. And therefore, at time equals 0, we have no excess carriers, which is exactly what we'd expect. We just turn the light on right at time equals 0. Now, what happens at the other end of the limit? What happens as time goes towards infinity? What will happen? Well, in this case, we can see that this last term here, this minus e to the minus t over tau p naught, that term is going to diminish down to nothing, and therefore all we're going to be left with is g prime tau p naught. And then so the next question is what happens in between the time t equals 0 and time t equals infinity? Well, in that case, we're going to have a logarithmic increase in the number of carriers with time. And writing a little plot here, we can see what that might look like. So as mentioned before, we start right here at 0, and we're going to end here at some value g prime t naught, tau p naught. So let's go ahead and write that there. And what happens in between is we have an increase. But as we have recombination, that increase rate slowly goes down and reaches this point up here. And we can actually know what that point is. We can look at the fact that g prime equals 5 times 10 to the 21, and that tau p naught equals 10 to the minus 7, and we can do a multiplication there. And we find that that equals 5 times 10 to the 14 per cubic centimeter. One of the things we might want to actually check is, well, if we remember this equation up here, our ambipolar transport equation, that was actually saying, that we have a low level of doping, or not a low level of doping, a low level of injection of excess carriers. And given these numbers, we actually do satisfy that. Look, 5 times 10 to the 14 is much, much smaller than our total number of carriers, 10 to the 16. This is, of course, assuming, which is true at 300 degrees, that the number of dopant atoms here is roughly equal to the total number of ionized carriers in the conduction band. And with that, that concludes this video of Unwired Learning.